Hi everyone, in this lecture I will be giving an introduction to Fourier series. Actually I have an Instagram account, a link is given in the description box below. There I will be sharing practice questions and notes every day. So please have a look at that account, and if you want you can follow that account too. So let's start. Okay. Now let's discuss something. Ancient Greek astronomers thought that the earth was at the center of the universe, said let this be earth, and the moon and the sun rotated around the earth in a circular fashion. Okay, that is what they thought. But the thing is that if the moon was rotating around the earth in a circular fashion, then every day our moon will be full moon, right? Or the moon will be the similar brightness every single day. But that is not the case, right? So when they looked into the sky, it is not the case. Every day the moon was changing its cycle. Someday it is half moon, someday it is full moon. Actually, it is going in a fashion, okay? And someday it is brighter, someday it is dimmer. So they concluded that that is not possible. If it is in a circular fashion, it is moving in a circular fashion, then it would have or every day it will be the same. But that was not the case. So they understood that there was something wrong with their theory. So what they did was, let's remove the sun for now. Instead of thinking that it is revolving around a single circle, they introduce another circle, okay, a smaller circle, and then they thought that the moon is over here. This circle is revolving on its own, like this, revolving. This circle is revolving around this orbit, and the moon is revolving around this smaller circle. Okay, that is what is happening. Uh, Still they didn't get a satisfactory result. Their theory was still not agreeing with the what they were seeing in the sky. So they introduced another circle over another circle, smaller circles, or small circles of different shapes and radius over one another. Okay, like this, circles over circles over circles, like this. Okay. So there was a lot of circles. So at some point their theory matched with what was seen in the sky. So what happened here? We all know that it is if the orbit is actually not circular in shape, it is elliptical in shape, right? But so what actually happened here? Circles over circles over circles is not an ellipse, right? But still we got the result, accurate result, as it would have been an ellipse. So what we can conclude from here is that any waveform or shape can be formed from circles over circles over circles. This is what Fourier said also. Okay, so let us draw the formula over here. So we know that we are talking about an moon following a circular path. Okay, so representing a circular path is orbit is z of t. Let z of t is equal to r into e raised to j omega t, where r is the radius of the circle. This is I am talking about a single circle. Then we will take into consideration so many circles. Okay, this is the angular velocity, the velocity at which this thing is moving. Okay, and now we'll come to circles over circles over circles. What happens when circles over circles? Obviously the radius will be changing, right? Circles over circles over circles, that the radius will be changing, and I have to write this equation for each circles or each orbits. Okay, each trajectory or path it is following. Okay, so it will be like z of t can be written as the final orbit of the end circle. Only the end circles path we will be considering. Okay, so please keep in mind that with this kind of circles over circles over circles, we can make any shape. Okay, we just have to take the particular velocity and radius. We can get any shape. So that is what Fourier said. Okay, now it will be like r1 e raised to j omega 1 t plus, because of the first circle will be having a certain radius and a certain velocity. Likewise, second circle r2 e raised to j omega 2 t plus r3 e raised to j omega 3t, etc. up to infinity. So I can write here like this. In generalized form, I can write here like this: z of t is equal to sigma k is equal to minus infinity to infinity ck into e raised to j, ck into e raised to j k into t, omega 0 k into t, because it will be changing with change in our suffix, right? So this is actually our expansion for what? Complex exponential Fourier series expansion, right? So Fourier stated that every possible waveform and function in existence can be generated by just adding together different sets of sine waves. Okay. So as far as we have studied, we are talking about circles. Okay. So we know that sine waves and circles and cosines are related. To make it that more clear, I will show an animation of a sine wave and its relation to unit circle, as well as a cosine wave and its relation to unit circle. Okay. Just wait. Okay. In this animation, it is traced around a circle. The movement of a body around a circle is traced, and the perpendicular component will represent, which is represented by a red line, will represent our sine wave, and the changes in the perpendicular component. Please have a look at the changes in the distances of the perpendicular component and how the sine wave that is reflecting in the sine wave. Okay, please see this animation. So as the length of the red line decreases, sine wave also decreases. Likewise, please, it is related. You can see that. Okay. So that is how a sine wave is related to a unit circle. And now let's see an animation for a cosine wave. Cosine wave and unit circle. Okay. Path around a circle is traced, and the parallel component of that will represent the cosine wave, and the changes in the parallel component, it is represented by a blue line. Please have a look at the changes in the length of the blue line and its corresponding wave, that is our cosine wave. Please, as we can see, the red line that is representing the sine wave and the blue line that is representing the cosine wave are 90° apart. We all know that. Just to make it clear. Okay. Now, what happens if a smaller circle is around a bigger circle and another smaller circle and another smaller circle? What happens? We'll see. So, look at this. Fourier stated that any possible waveform and function in existence can be made by just adding together different sets of sine waves. So here the sine waves are represented by our circles only, and in the last picture we can see that the circles are overlapped around one another. Okay, so the individual traces of the circle is given, and what happens when the circle is wrapped around another circle, another circle, another circle. We will see if we can generate another waveform by adding together so many sine waves. Please have a look at this animation. the last circle's path is traced. Okay, always. So what does it represent? It represents a square wave. So by adding together different sine waves of a different coefficients, we can say different sine waves of a different radius and different amplitude, we can generate another periodic waves. That is being proved in this animation. Okay, now let's take another example also. It is about the Dirichlet's condition. That is a condition for the existence of Fourier series. Okay, the first condition is the signal should have finite number of maxima and minima over the time period. Signal should have finite number of maxima and minima over the time period. I will give an example here. So let this be a signal and let the time period be t0. Okay, over the time period we will see how many maximums and minimums are there. This is one maximum, this is one minimum, and this is one maximum. Okay, and this is one minimum. How many maximums are there? 2 maximums and 2 minimum. They are finite, right? So first condition is this: there should be finite number of maximums and minimums over a time period. And the second condition is the signal should have finite number of discontinuities over the range of time period. The signal should have finite number of discontinuities over the range of time period. So I will give an example. So this is t0. How many discontinuities are here? 1, 2 and 3. Over the time period there are 3 discontinuities. It is finite. So that is the second condition. And the third condition is signal should be absolutely integrable over the range of a time period. Condition number 3, signal should be absolutely integrable, that too over the time period t0, say t0. So these are the next condition, the last condition, the signal should be bounded. Okay, so these are the 4 conditions for existence for a Fourier series. And with that being said, I am going to end this video. In the next lecture we will be discussing about trigonometric Fourier series and how the equations are coming into being, the formulas are coming into being. So please have a look at my Instagram account too. There I will be sharing these notes, the notes that I have written in that, and also some practice questions are daily uploaded. So it will be helpful, I think. Please have a look at that too. Thank you for listening. Have a nice day.